In this lesson, we are going to learn how to analyze exponential functions. Specifically, we're going to look at growth and decay functions. An exponential function is in the form of f of x equals a times b to the x power. And there are some conditions on this, where a cannot be 0, because if it were, this would just be a constant function. It would all equal 0. B has to be positive, and it can't be 1. Now, a is also called the initial value of your function. It's the value of the function when x is equal to 0. Where b is referred to as the base. This is also going to be, just looking ahead, our growth or decay factor. That'll help you when you're in looking at word problems and applications. So what we're going to do is we're going to start looking at exponential growth functions, and we're going to look at what they look like graphically and analyze them from a calculus perspective. So we're going to begin here by analyzing y equals 2 to the x power. So to do this, let's quickly make an xy table. So if I plug in some values for x, well, if I plug in -2, this would be 2 to the -2nd power, or 1/4. If I plug in -1, that would be 2 to the -1st power, which is 1/2. If I plug in 0, that's 1. 2 to the 1st is 1, 2 to the 2nd, 2 to the 1st is 2, and 2 to the 2nd is 4. So I'm going to quickly graph these points, and you can see I get this curve. And it starts to grow really, really quickly. If I went up to 2 to the 3rd, that would be 8. I'm going to label this as y equals 2 to the x power. Let's now look at how does it change if I have y equals 3 to the x power. I'll do this one in red. So 3 to the -2nd would be 1/9. To the -1st would be 1/3. To the 0 would be 1. To the 1st power would be 3. To the 2nd power would be 9. Plot these values. It's going to be, let's see, 1/9. It's going to be right here. 1/3 about here. So on top of this point, then 1, 3, 2, 9 is going to be up here. So look at how this is growing more dramatically. It's going to get steeper and steeper. Notice that they both cross through at 0, 1. Now let's look quickly at y equals 4 to the x power. I'll use the same points. This will give me 1/16, 1/4, 4 to the 0 would be 1, 4 to the 1st is 4, 4 to the 2nd is 16. So we will graph these, and this is going to be growing at an even faster rate here. It's going to be way up there. All right, so let's now analyze, let's see what we've got going on here. So my domain, how far left and right, that's going to go from -infinity to +infinity. But what about the range? Well, for this function, it looks like I've got a horizontal asymptote. It's approaching 0. So 0 to infinity is going to be my range. How about symmetry? Do I have even or odd? Well, that's going to be neither symmetric about the origin, nor is it symmetric about the y-axis. About continuity, it is continuous on the entire range. There's no breaks. It goes from -infinity to +infinity. Increasing, it is always increasing from -infinity to +infinity. How about any extrema? Well, it doesn't have any. It just continually increases. We've got no peaks or valleys, so I'm going to say none. How about x-intercepts? Well, that also has none, or they do not exist. It's not going to cross the x. The y-intercept, notice that they're all crossing at the point 0, 1. Vertical asymptotes, I do not have any. Horizontal asymptotes, I think you're seeing that it's approaching the y-axis. So I have a horizontal asymptote at y equals 0, and now let's talk our end behavior. So on the left, it is approaching 0, but on the right, it is approaching positive infinity. So the limit of f of x as x approaches infinity is equal to infinity. Let's look at how these graphs change if the base of our function is a value smaller than 1. It's going to be exponential decay if your base is between 0 and 1. Remember that your base cannot be negative in an exponential growth or decay function. So let's first look at y equals 1/2 to the x power. If I raise 1/2 to the negative second power, that would be 4. 1/2 to the negative first power would be 2. To the 0 power is always 1. 1/2 to the first power is 1/2, and to the second power is 1/4. I'm going to graph this curve. So I've plotted these ordered pairs and sketched my function. I can already see exponential decay. I can see the rate at which it's decreasing very, very quickly. So let's look at y equals 1/3 to the x power. So if I substitute in -2, 1/3 to the negative second power would be positive 9. To the negative first power would be 3. To the 0 power would be 1. To the first would be 1/3, and then 1/9. So to quickly plot these, I see that my curve is decreasing at an even faster rate. And finally, y equals 1/4 to the x. Let's analyze the same points for this function. So to the negative second power would be 16, then 4, 1, 1/4, and 1/16. Let's plot those and sketch my curve. And again, I see that it's decreasing at an even faster rate because that base is smaller. Okay, let's talk our analysis. So our domain, again, is negative infinity to that should be a comma, to positive infinity. The range would be 0 to infinity. Symmetry would be neither, even or odd. Continuity, it is continuous from negative infinity to infinity. It is decreasing for the entire domain. There is no local extrema, never crosses the x-axis. The y-intercept, notice, is the same. No vertical asymptotes, and I have a horizontal asymptote again at y equals 0. And my end behavior will be the limit of f of x as x approaches negative infinity is approaching, and I just realized I've got a mistake here. That should be, it's approaching positive infinity on the left, and it's approaching 0 on the right. So how does this change from our previous exponential growth function? Well, it just so happens when it's an exponential decay, it's decreasing, and the end behavior is reversed. Everything else is the same as far as analyzing from this calc perspective. Let's take a second and look at the natural base, which is known as E. It's also called Euler's constant. And I would encourage you to watch the video I've linked that shows you a great explanation of what this number is. It's a constant, just like pi is a constant, or that's 3.14159, which is based on a geometric concept. E is the number approximately 2.718. Again, it's irrational, so it goes on forever. And watch the video for a great explanation of what it actually is. Here's the mathematical definition of it, and it's known as the natural base. So the function e raised to the x power is also called the natural exponential function. So it's exponential growth. It still crosses at 0, 1, but then if we were looking at, what is it? If I plug in 0, I would get 1. If I plug in 1, I get the value e, which is approximately 2.718. So that's where this value is right here, 1e, but it's still increasing. Okay, we're going to look at transformations now to graph some exponential growth and decay functions. Since we looked at our basic functions, And in this course, we've always been performing our transformations in the order of AHBK. So A is the value that is in front of our exponential growth or decay function. So if A is negative, it's going to reflect our function across the x-axis. If the absolute value of A is greater than 1, we will have a vertical stretch. If it's less than 1, we'll have a vertical shrink. H, which is something that's added or subtracted onto our x value in our function, so you'll see it in exponential up here in the exponent spot, is always a horizontal shift or translation left or right. And if you remember, whatever happens to our x value or horizontal shifts and stretches and shrinks, they always work opposite of what we think. So in other words, if I would have y equals 2 to the x plus 4, that would shift it 4 to the left. Whereas if it's minus 4, it's going to shift it 4 to the right. Okay, our b value, and what can be a little confusing here is I switch this to a capital B where this is the base of my exponential function. So if there's a little b, a coefficient in front of our x here, that's going to be a horizontal stretch or shrink, but we also have to consider if it's negative. And just like before, if it was negative, it would be a reflection across the y-axis. And when I'm saying just like before, I mean every other function that we have looked at in this course, the transformations really work the same, which is one of the beautiful things in mathematics. So if the absolute value of b is greater than 1, so normally we think that that's a stretch, but because we're talking horizontal, it's actually a shrink. It's a horizontal shrink. We always say by a factor of 1 over whatever that b value is. So it's like the reciprocal. Now if that b value is a fraction, this is where again it's a horizontal stretch by a factor of 1 over b. So if it were 1/4, you'd say it's a stretch by a factor of 4. And finally, our k value is a vertical shift up or down. So the vertical stuff kind of just like works the way you think it is. It's the horizontal stuff, that h and b, that whenever it's happening to your x value kind of works opposite of what you think. Let's put this into practice. So we're supposed to describe the movement of the graph of f of x equals e to the x. So this is your natural exponential function. It has a base of e, that 2.718, and we are to include direction and magnitude. And we want to do this in our order. We always say AHBK, all hail Burger King. I have a value and it's negative, so I'm going to begin by saying there is a reflection across the x-axis. And then since my a value is, the absolute value of it is larger than 1, there is a vertical stretch by a factor of 2. So these two are my a. I look for an h value, and I do. That's whatever is added or subtracted to my x. So my h is 3, and so that implies a horizontal shift, and it's opposite of the direction I see. So horizontal shift left 3 units. There are no other values. I don't have a b or a k, so I can move on to my second one. So in my second one, again, it's my natural exponential function. There's no a value, meaning no coefficient in front of the e. I go to h. There's nothing added or subtracted to the x. B value, I do have a -2 there as a coefficient. So this affects it horizontally, so I have a reflection across the y-axis. And then I have a horizontal, now it's larger than 1, so it works opposite of what we think, so it's a horizontal shrink by a factor of that reciprocal, by factor of 1/2. And then I have this +3 at the end, so AHB, that's going to be my k value, and that makes it vertical. I always think k vertical, that hard k sound, even though it's a c. But it's a vertical shift, and it's going to go up 3 units. Vertical stuff happens just as we would expect. So a plus is going to make something go up. A large value is going to stretch it. Okay. Let's kind of switch directions here. Our next one says, write the equation of the function g of x whose graph is described. So we're told that f of x is our natural exponential function. It's vertically shrunk by a factor of 1/4. All right, so let's start by saying g of x equals, so vertical shrink is my a value, so that's going to come out front, e to the, then the graph is reflected across the x-axis, so that's a vertical reflection, so that's going to make this negative. And then finally, it is shifted down 7. So down 7 is going to have this -7. Need my x and my exponent spot. And there we go. All right, moving on. The graph of f of x equals e to the x is shifted to the right 1 unit. All right, so my new function shifted to the right. Means it's happening to x. So shifted to the right would be -1 because it happens opposite of what you think. Then the graph is horizontally shrunk by a factor of 1/3. So I'm going to put the reciprocal in front of x, so I'm going to write a 3. And then finally it's shifted up 2 units. So it's going to be +2. Perhaps I should have mentioned this first, but sometimes it's easiest off on the side, you put your A, H, B, K, and you list what's given to you. So kind of think it through one more time for you. Shifted to the right 1, that's going to make my H value, horizontal shift to -1. Vertically shrunk by a factor of 3, or 1/3, so the reciprocal of that makes this 3. And K, vertical shift up 2 units, so +2. All right, and then you would fill it into your function. Okay, the last skill we're going to do here is we're going to use our knowledge of transformations to sketch our basic graphs. If I just think about y equals 2 to the x would be my parent function here. And at the start of this, we just plugged in some values. We did -2, -1, 0, 1, and 2, just to get some idea of what it looked like. And we had 1/4, 1/2, 1, 2, and 4. All right, now let's think about our transformations. So we have a vertical stretch by a factor of 3. So I'll be multiplying each y value by 3. I also have a horizontal shift right 1, which means each x value will have 1 added onto it. And then I have a vertical shift down 4, which means I now have -3.25 for my new y value. And to make it a little clearer, I'm just going to, I think, recopy my ordered pairs over here. So my new one will be -3.25, then it would be -2.5. If I multiply 1 times 3 would be 3 minus 4 is -1, 2 times 3 is 6 minus 4 is 2. And 4 times 3 would be 12 minus 4 would be 8. And then as far as my x values, they're each just shifted 1 to the right, so it would now be -1, 0, 1, 2, and 3. So if I graph these ordered pairs now for my transformed function, I will get a function where the horizontal asymptote would be shifted down 4. It's typically at 0, but it's going to be shifted down 4 units because of that vertical shift down. And I'm just going to plot my other ordered pairs. 0, -2.5, 1, -1, 2, 2, and 3, 8. So my curve, exponential growth, will look like this. So my domain, let's see, would be from -infinity to +infinity, as all exponential growth functions are. And my range would be now from -4 to infinity because of that vertical shift downward. So I'm going to look at another one, and I'm just going to consider my function y equals 3 to the x power with just a base of 3, and figure out what these points are, and now I'm going to transform them. So my a value would be -1, which means I have a reflection over the x. Which means each y value will be multiplied by -1. So I'm going to multiply this column by -1. And I have a vertical shift down 2, which means I'm going to then subtract 2 to each of my y values. So my new ordered pairs, the x's, there'll be no change in those. So -1, 0, 1, and 2. But my y's will become, let's see, be -2 1/3, -3, -5, -11. And now I'm going to graph those values. I'm just going to also consider my horizontal asymptote will be shifted down 2. I've got a reflection. I'm going to graph these values. And this one's going to be way down here. So my function will look like this.